This is the map of mathematics. Most students start around here, learning basic intuition of numbers and the arithmetic operations, and from there build up their knowledge of mathematics, from algebra to geometry and trigonometry, vectors, and eventually calculus and beyond. However, just like constructing an actual building, the most logical starting point of mathematics should be with the foundations, the most important of which being the topic of today's video, set theory. My main goals for this video are fairly simple. 1, to provide a basic understanding of what a set is, and 2, to explain the most important operations surrounding sets. Without further ado, this is an introduction to set theory. To start this video, we formally define a set to be any unordered collection of distinct objects, called elements, which can be well defined. Now, that's a mouthful, so to get a better feel for what this looks like, let's look at an example. So, you're walking down towards your favorite store, the number store, and with what money you have, you buy your 3 favorite numbers, let's say 1, 2, and 3. Now, as you can see, the numbers in this box are both unordered and distinct, which makes them a perfectly valid set of numbers, where the numbers themselves are what we call the elements of the set, simply meaning that they are in the set. You would denote that a number is an element of the set with this symbol, and draw a cross through it for numbers which aren't elements. Okay, we're going to label this set, and the common practice is that sets are denoted with capital letters, so we're going to label it capital A. The regular notation to write out a set is in a list, like this, in what is called roster notation. Again, the set is still unordered, so we can rewrite it like this, or any other order we like. Let's introduce a new set, B, which will represent the total stock of the store. It should be obvious, then, that all of the elements of A should by definition also be elements of B, with some extra elements left over. When this happens, we can call A a proper subset of B, which we would denote like this. If we were to change A or B such that they contain the exact same elements, A would then just be an improper subset of B, or even more simply, just equal. For cases where writing sets in roster notation are impractical, mathematicians created another way of describing sets, called set builder notation. Set builder notation is a way of building sets based on some condition, rather than writing out all of the elements. The general form looks like this, where S is equal to the set of all elements satisfying some conditions, where this colon means such that. For example, let's say we wanted to write the set of all square numbers, starting at the number 4. This, of course, could not be fully expressed in roster notation. Well, to start, we would find a function or sequence which describes this pattern. In this case, it's pretty clear that the nth term in this set, which I will denote a sub n, is equal to n plus 1 squared, and you can verify this pretty easily by plugging in values. Therefore, the first part of the set builder form of this set will be a equals n plus 1 squared, and the conditions used to generate this sequence will simply be that n is a natural number. A common misconception for new learners is that sets can only contain numbers, which couldn't be further from the truth. In fact, part of what makes sets so powerful is that they can contain anything, including shapes, people, or whatever else you can concretely define. They can even contain sets themselves. Now, if I take out this smaller set, call it B, then I want to ask you a question. Which of the following statements is correct? Is 1, B a member of A, or 2, B a subset of A? Please pause to think about this. The answer is, of course, 1. B is a member of A. Why? Well, when you have a set which contains other sets, those smaller sets, in this case B, are treated as a single element of the larger set, A. If you wanted to correct the second statement, you could say that the set containing B is a subset of A, as this set is now a collection of elements in A rather than an element itself. Now that we have the basics of sets down, we can start looking at operations we can use on them, namely union, intersection, and complement. Let's say we have two sets, A and B, where the elements of each set is the infinite collection of points within their boundary. So, for example, this point is a member of A but not B, this point is a member of B but not A, this one of both, and so on. Firstly, the union of two sets, A and B, is defined to be the set of elements that are a member of either A or B. And this is why I want you to think of union as an OR operator. Its denotation looks like this, which I personally like to remember as a U for union. In our picture, A union B would be all three regions of our Venn diagram, as each section consists of points of either A or B. The set builder notation for union looks like this, where A union B is the set of all points X such that X is a member of A or a member of B. Secondly, the intersection of two sets, A and B, is defined to be the set of elements that are a member of A and B. Again, just like union is an OR operator, intersection is an AND operator. This is denoted with this symbol, which I like to remember as an N for intersection. In our diagram, the intersection of A and B would be solely the overlapping region, as those are the only points in both A and B. Its set builder is the same as union, except we simply swap the OR for an AND. Now, if we move these sets apart so that they don't share an overlap, now what would their intersection be? Pause if you'd like to think about it. Well, because there are no elements which are in both A and B, their intersection has to be a set which contains no elements. This set actually has a special denotation, and it's called the empty set. When the intersection of two sets are this special set, we call A and B disjoint. Lastly, the complement of a set A with respect to another set S is the set of elements which belong to S but not A, making complement the not operator. Complement has two denotations, the first being read S minus A, and the second reads simply as A complement, which is used as shorthand only when it is already clear to the viewer which set A is being taken complement with respect to. In this case, let S equal A union B, which again is the whole Venn diagram. S minus A, or alternatively just A complement, is equal to just the blue disk, because those are the only points in the Venn diagram which are not a member of A. Its set builder notation is the set of all points X which are a member of S, but not A. It's worth noting that when we use this notation for complement, the set we are actually taking complement with respect to is called a universal set. Vice versa for B. S minus B, or B complement, is simply just the red disk, and its set builder notation is the set of points which are a member of S, but not B. That's all the notation I want to teach for this video. However, I would like to conclude by talking about a pair of theorems which combine all of the topics we learned today, and those would be something called DeMorgan's laws. DeMorgan's laws state that if you have two subsets, A and B, of a universal set S, then 1. The complement of the union of A and B is equal to the intersection of their complement, and 2. The complement of the intersection of A and B is equal to the union of their complement. Let's look at the first theorem first. Using what we just learned about these set operations, we know that this set is equivalent to the set not containing A union B, which is furthermore equivalent to the set not containing A or B. It should then logically make sense, and verify this for yourself if it doesn't, that the set not containing A or B should be equivalent to the set not containing A and not containing B. And likewise for the second theorem. A intersect B complement, or equivalently the set not containing both A and B, should also be equivalent to the set which neither contains A or B. Let's look at an example of this. Let S be the set containing the following regular polygon, where A is the set just containing the square, and B is the set containing the hexagon and octagon. Let's look at Theorem 1. Firstly, A union B is just the shapes that are in either A, which is just the square, or B, namely the hexagon and octagon. The complement of this set is then just the shapes which are in S, excluding those in A union B. As for the right side of our theorem, A complement is just the set of shapes in S, excluding those in A, and B complement is just the set of shapes in S, excluding those in B. Therefore, A complement intersect B complement is the set of elements which are in both of these two sets, namely the triangle, pentagon, and circle. And as you can see, we have verified the theorem for this example. But that'll do it for this video. Thank you so much for watching. This has been my entry for 3 Blue and Brown's Summer of Math Exposition, so if you enjoyed this video, I highly recommend you check out some of the other submissions. See you later.